Okay, cool. All right, here's just a general agenda for the day. Yeah, we don't need to look too far into it, but we're just going to start with high-level design first. Yeah, so a little bit overview of the prop team. Anything I need to be worried about?
I'll stay up there just to monitor the call.
Okay, cool. So yeah, our team is a team of multidisciplinary engineers with an enthusiasm for rocket propulsion. We have a wide variety of academic experience. So we have first years to fourth years and kind of fifth years as well. We have strong industry roles and connections. All the companies listed there are, we have either everyone on our team has either been employed or will be employed soon by those entities there. Then we have an emphasis on collaboration and teamwork here. And obviously Cal Poly's learn by doing policies and mantras. All right, so this is again high-level design. So the mission goal is to gain meaningful understanding and practical experience of liquid rocket propulsion through a small, scalable bi-propellant rocket engine. Here is an exploded view of our system. So we'll get into every one of these components, but combustion chamber nozzle over there on the right with a retaining ring, some sealing O-rings, the injector plate with the interface plate, and fasteners all the way on the left. All right, so here's some basic parameters. Some of these were set by our department or just club goals. So we have 90% ethanol and nitrous oxide for the propellants. We chose ethanol here because we can dope it with water if we have any heating problems or thermal problems during testing. We have a thrust of 25 pounds, a chamber pressure of 145 psi, no cooling method. So the copper engine is entirely a heat sink, pressure fed, and a burn time of 3 seconds. And I'll think a little. Okay, then so to determine a lot of the combustion characteristics, we used NASA CEA, RPA for a lot of the sizing, and as well as our own design code. So to generate a lot of these combustion gas characteristics, we kind of inputted those, what you see above, in the design code and in RPA to verify a lot of the geometry of the chamber. And on the right, you can see a couple curves with our operating point. Is the point on the red. Obviously, with our mixture ratio of 1.5, the combustion temperature is significantly less than stoichiometric. But we did that purposely because we think that the thermal constraints of our system will be most pressing. And you can also see that we are not as efficient as we'd like to be with that mixture ratio of 1.5. But again, we really were trying to minimize the thermal requirements that our system has to undergo. Yeah, I think with that, I will bring up the combustion chamber team, and they'll get more into a little bit of the component level design for a lot of these systems.
All right. Hello, everyone. I'm Jake Huff. I am the responsible engineer for the combustion chamber and the nozzle, and I guess I'm gonna get into this. So first, in terms of high-level overview, for anyone that's not familiar with what a combustion chamber and a nozzle really do in a rocket engine, the idea is to just kind of turn the thermal energy from the combustion into kinetic energy via the geometry of the chamber profile. And essentially, this just speeds it up until you get to Mach 1 at the throat, which is the thinnest portion of the combustion chamber profile. And then it expands to achieve even higher velocities. Our exit velocity is around Mach 2.3. And yeah, so first things first, as Adam said, we have no cooling method, which means that our combustion chamber and nozzle are collectively a heat sink, which basically just means all the heat from the combustion that is transferred to the walls needs to be absorbed, and it needs to be able to withstand that thermal load along with the mechanical stresses that it will be enduring due to the pressures within the combustion chamber. We chose to use copper 110 for our material, and this is going to be machined entirely as one singular part. So we will be talking about manufacturing later, but that's going to be a fun event. Anyway, the major interface that we have is with our compression flange that attaches the injector onto the left side of the cross section as it's shown on the slide. And that beveled portion is meant for the flange to attach around. In terms of significant geometry, most important thing is probably the throat diameter. It's going to be about 0.374 inches, which is rather small, but that's a function of what our thrust goals and chamber pressure are. And aside from that, the whole cylinder has a diameter of about 2.1 inches and is about 4.5 inches long.
Expected operating pressure?
About 10 bars, so 145 PSI. Anyway, so in terms of nozzle, we have designed it for ideal expansion at sea level, 1 atmosphere, right? This isn't a flight engine, so we want it to just be ideally expanded as we're testing it. And that meant that we have an expansion ratio of about 3.25, which is the ratio of the throat area to the exit area of the nozzle. And we chose to have a conical nozzle with a 15-degree half angle. This is kind of like the unofficial reference for conical nozzles, and it's a lot simpler than a bell nozzle, but has very minimal losses, so it's deemed acceptable for us. You can see on the charts that we have the profile of the chamber on the top, and then on the bottom, they're shown so that the x-axis, the length along the chamber, is reflective of each other, and you can see kind of how the local Mach number increases throughout the chamber. Next, okay, so for high-level combustion chamber design, we chose, but also researched a characteristic length, or an L star, of 55.1 inches about, which is 1.4 meters. And this is something that generally hydrocarbons are around roughly this region. There is a range, of course, but 1.4 was, through feedback from our PDR and through our research, what we deemed to be a good choice. Throat diameter, as I said before, is 0.374 inches. And we have a contraction ratio of 1:16, which is pretty high, but for a thruster this small, that is fairly normal, as can be shown on the graph on the top, which pits throat diameter against contraction ratios, was found in one of our propulsion textbooks. Yeah, our overall chamber volume is about 6 inches cubed, and then the convergence angle from the chamber to the throat is about 45 degrees, just some chamfers and other curvature, but that's the general geometry. And then we have a wall thickness of 0.3 inches, which will be important later. That's in reference to the thinnest portion between the actual cylindrical region of the combustion chamber and the outside of the entire copper cylinder. Yeah, next I'm going to bring up Matthew and Ethan to talk about material selection.
So in determining which materials we wanted to use, as we are using our actual combustion chamber as a heatsink, we prioritize thermal conductivity over all else. So we have our melting point, our thermal conductivity, which is what we consider most, and the tensile strength and material with nitrous oxide, which is a part of the fuel. We determined that copper 110 was the best choice to use, as it has the highest thermal conductivity and the flames will not melt through the copper.
Yeah, so all of our information is from MatWeb. Most of those values are assuming room temperature. The material compatibility is with nitrous oxide. So we chose copper 110 due to the satisfactory nature with those combustion fuels, and those were our main considerations in this selection. Thanks.
So next, as I said before, we are using a heat sink as our quote unquote cooling method, which essentially means that our chamber is never going to reach a thermal equilibrium while we are actually, doing our burn. And is a function. That's also why our burn time is only 3 seconds, pretty short. But to do a heat transfer and thermal analysis on this chamber, I used a equation. It's called the Bart's equation. It's used for estimating the convective heat transfer coefficient. And the reason that I chose this is because in a combustion chamber like this with the really fast moving gases, you kind of can neglect conduction and radiation in comparison to like the magnitude of convection. So really that's our most important mode of heat transfer. But essentially the way this was done was iterating along the inner profile through time. I was able to look at what the convective heat transfer coefficient was and the amount of heat that was transferred in. And then by iterating through the copper and looking at the conduction, we were able to find the thermal profile for the whole thing. And yeah, so on the bottom left, that is what the temperature, I guess, distribution will look like in the combustion chamber at the end of our 3-second burn. As you can see, it's rather high directly at the throat, about 1350 Fahrenheit. But the actual chamber walls, the thinnest portion that I was talking about earlier, it's only going to be about 400 degrees Fahrenheit. And this is well below the melting point of copper 110, which is about 1949 degrees Fahrenheit. Yeah, and in terms of mechanical analysis, the wall thickness, as I said, was chosen to be 0.3 inches for the thinnest portion. And this is where we're going to see our highest mechanical stresses, as this is where our highest pressures are and our thinnest wall thickness. And we looked at this portion with the temperature gradient in mind, but it's only about 20 degrees different between the inside wall and the outside wall. So the actual stresses that come from that are fairly minimal. Which meant that we were able to analyze the chamber as essentially a thick-walled pressure vessel, and looked at the Tresca failure criterion due to its conservative nature. On the right, on that graph, you can see the different stresses, the hoop stress and the radial stress throughout the thickness of the wall. And then the yellow line is the maximum shear stress, which is what the Tresca criterion is looking at. And so copper 110 has a yield stress of about 30,600 PSI at room temperature and at 400 degrees Fahrenheit, which is what we're expecting the walls to get to. It's about 28,000 PSI, so a little bit lower, but not too significant, which meant that we have a pretty large factor of safety at about 52, which we're essentially not really concerned about any sort of mechanical failure of the chamber itself, which means that this is going to be a safe system. The only worry that may be, I guess the only issue that may present itself is with the throat, as we're getting to a much higher temperature of about 1350 Fahrenheit, which could allow it to yield a little bit between burns. Hopefully that will not be a huge issue. We'll be able to fire this several times, but there is a chance that it will experience a little bit of warping on the contour. And next, I'm going to bring up Paige and Hina for talking about Igniter.
Okay, so we have 2 Igniter ideas, and we're going to make a final decision based on testing going forward. So our option A is to machine into our combustion chamber to integrate a cartridge with an A-size solid motor in it. And we're going to machine this cartridge out of aluminum, and you can see in the exploded view and the top right the CAD for that cartridge. And in combination with the machined cartridge, we're going to be using a stainless steel pipe nipple and a high pressure galvanized steel pipe fitting to integrate that into the chamber.
So they will be threaded together, but we will also be using Teflon sealing tape for additional thread sealing. Our further testing will include pressure testing and hot fires, and it will be an ignition with a 12-volt battery.
And then for our option B, an electrically activated B-size motor that would be inserted into the nozzle, and we will also ignite that with a 12-volt battery. and the flame will be shot up the nozzle to ignite the propellant gases.
We are working with a senior design project that is using this option, so we'll be working with them to ensure safety and reliability if we follow through with this. We've also worked with other experimental rocketry groups of mounting the fixture to the back of the nozzle, but we do need further validation and testing in order to integrate this option.
Okay, I guess first I just want to ask if anyone has any questions. I know this has been a lot of information pretty quick. Okay, awesome. Well then, oh, yeah. The plan as it stands is to do that on the lathe during one of the operations. Which actually brings me to the manufacturing plant conveniently. So the plan right now is, oh, sorry. What? Yeah, I can't see it. It's in the chat.
No, I don't know if it's supposed to. So you can just continue.
Okay. Okay, cool. So for manufacturing, currently the plan is a little bit loose, but our current intention is to use Cal Poly has a CNC lathe located at a shop at the airport, just about 20 minutes from here. It's a Haas TL1 CNC lathe, and our plan is to buy 2 3/4 inch diameter copper 110 stock. And then we are going to essentially drill and then bore the nozzle in the combustion chamber cavity as separate operations. We're going to have to flip it around. So we'll have a minimum of 2 operations. We're shooting for 2 collectively, just so that we don't have to do too much like re-gripping, because that can mess with the tolerances. And in terms of like what we're trying to really achieve, we have a couple ultimately very critical dimensions. First one is the nozzle throat diameter. That one's important because we have to have it be small enough, but not too small. Otherwise, it's going to mess with the gas dynamics within the chamber. And so we're trying to target, Mach 1 hitting supersonic at the throat, as is the point of a nozzle. So that's important. And then aside from that, the interface with the injector and the compression flange are very important. So the bevel portion on the left is going to be of utmost importance. So we're going to have fairly high tolerances on that, which are yet to be set. Yeah. And then last, talking about testing. Combustion chamber itself is probably going to be tested mostly fully integrated with the rest of the assembly. This will mean that we're going to have to pressure test the entire thing. And if we do have a wall integrated igniter, that's going to be a seal that we're going to have to put through pretty rigorous pressure tests in order to make sure that we're not spewing hot gases out the side of the chamber. And so we'll do water flow tests and stuff when they're all attached, just to ensure that the seals are good. And then we'll probably also check with cold flowing propellants through to check for the corrosivity and other potential issues that we may run into. Yeah, I guess want to ask one more time. Yes.
Is that about how you're going to seal if it's the wall injected igniter method?
Right. Yes. As they were talking about, it's going to be
Threaded as well as Teflon.
Yeah. So we'll use tape essentially as almost like a thread lock around. So once it's screwed in, it should be, I guess, tight at the high elevated pressures that we're going to experience.
And then also, is there a testing plan for deciding which of those igniter methods you're going to use? Like, what test are you going to run to decide which ones you want to use?
I think the first option we presented is going to be our first option unless something goes wrong with that. I know the senior design team is working on testing for the second option, but for the first option, just pressure testing that and hot firing it to make sure it would work well integrated into the chamber.
Yes, I believe as far as for the future, also this form of ignition is something that's used pretty commonly for engines of this type and larger ones. So we want some amount of experience with that as well, which is part of why we're leaning for an option A. Yes, Tanish.
Question from the chat.
Okay.
Are you planning on incorporating any instrumentation into the nozzle itself?
There has been discussion about inputting some pressure sensors mainly into the combustion chamber to ensure that we're actually meeting our intended chamber pressure. And then I'm sure we will also have thermocouples, probably on the outside though, that we can then use our temperature model in combination with the actual data to perform an estimation of the combustion temperature on the inside. That's probably the extent of our instrumentation that we'll have. That is still subject to change. We're kind of figuring that out as we go. Anything else? Okay, awesome. Well, thank you, everyone.
That's from, this is kind of.
All right, so the injector is the second part of this presentation. The injector is the most mechanically complex part in this assembly, and it's one of the most important. And we're gonna get into it right now. My name's Aiden Kaplan, and I'm the responsible engineer for the injector. So just to go over a little outline of what we're gonna talk about, we're gonna start with some requirements. Then we're gonna talk about the major design changes that we've made since PDR. Then we'll talk about the high-level design, then the individual physical design of the plates. Then we're gonna talk about sealing, then material selection. Then we're gonna talk about our manufacturing plan and then our testing plan. So to start it off, just a general overview of the purpose of an injector. The injector will accept fuel and oxidizer lines from the feed system. So fluid is routed into the injector from the propellant tanks through a bunch of valves. We'll get to that later. And it distributes fluid into several different channels. Depending on how many element types you want, this manifold can, or how many elements you want, this manifold can be extremely complex. And with the type of injector that we're using, which is an impinging jet injector, the manifold will shoot the propellant streams out angled at an angle so that they will hit each other. And liquid propellant streams hitting each other, you're going to have vaporization because it'll create really tiny droplets with a lot of surface area. With the high temperatures of the combustion chamber, it will be conducive to vaporization or evaporation, and then atomization, and it'll be conducive towards combustion. The injector also needs to drop the propellant pressures to the combustion pressure, as there will be pressure drop inside the injector, and the pressures in the feed system are far higher than the pressure we want inside the combustion chamber. So the injector will facilitate that pressure drop. And additionally, the injector must not create any interpropellant mixing inside the injector. So no mixing fuel with oxidizer, because if you do that, then in combination with the hot combustion gases, you're going to blow up your engine. So we will not be doing any of that. Finally, we need to the injector needs to be able to hold at least 750 PSI because that is the assumed inlet pressure to the injector. So just needs to physically withstand the pressure. So this is the high level design for our injector. We have a mixture ratio of 1.5, which Adam touched on in the, I think he touched on it in the initial high level design. The purpose of the 1.5 mixture ratio is to lower our combustion temperature. So we're kind of just working with the combustion chamber team on that because we're using heat sink cooling. We're using an unlike quadlet element with 3 fuel holes and 1 aux hole. The impingement angle is 45 degrees. So the 3 aux streams, as you see in that picture, sorry, the 3 fuel streams will exit at a 45-degree angle and all impinge at one point with the center aux stream, which is vertical, which is shooting up vertically. Additionally, that straight line distance that the propellant is traveling is 0.528 inches. This is recommended to be 5 to 7 times the average diameters of the fuel and aux holes. And so as you can see in that table, we have our orifice area, our orifice diameters outlined. So for the fuel orifice, we'll have a diameter of 0.043 inches, which corresponds to a number 57 drill bit. And for the aux hole, we will have a diameter of 0.098 inches, which corresponds to a number 40 drill bit. The areas and therefore the diameters of the orifices were calculated using the equation on the right, which is from Sutton. And we assumed a discharge coefficient of 0.8 when we did this calculation, because we used this type of orifice that's on the bottom right. The conical, I forget what, yeah, short tube with conical entrance. Yeah, okay. Yeah, and so you can see in that table, we have a bunch of discharge coefficient values that are dependent on the orifice diameter. Since doing this calculation, we didn't actually know what the diameters were going to be. We just picked a value of 0.8 because it's around where all of them are. Are there any questions on the high level design? Yes. Yes. Yes, we'll get into that later, but yes, they are. Are there any other questions? Oh, the vent holes. Yes, I will get to that. That will come in our sealing section, but essentially, we have a double O-ring seal between the two between the aux and the fuel holes, and the vent hole is placed between the two O-rings so that if a single O-ring breaks, the pressure will vent through that vent hole and into the combustion chamber instead of pressurizing the second O-ring. So it's single fault tolerant. All right. Any other questions on the high level design? All right. So I want to go over some major design changes we've made since PDR. If you remember what our design looked like at PDR, you remember it was extremely different. We have changed it a lot. And we've also learned a lot in the past few months. So the biggest change is definitely the element type. So back in PDR, we were presenting a 2-on-2 unlike quadlet, which basically we had 2 fuel holes and 2 oxidizer holes that would impinge together in sort of like a plus formation. And we would have an igniter in the center of the 4 orifice holes. Because of issues with the igniter that we've discovered that we were planning to use just a spark plug that apparently has issues with the prop lab, and Cody, our lab tech, has had many issues in the past using this spark plug. We decided to move away from it to the current configuration that was explained in the previous slides. So since we changed our igniter plan, we no longer had to put the igniter in the center of the plate, and therefore we could switch element types to what we currently have with the single aux hole in the center and the 3 fuel holes on the outside. This design change allowed us to simplify our design. Before, we were using a 3-plate design with like 2 levels of propellant channels. The first level would route the fuel to its holes, and then the second level would route the aux to its holes. But the design change has allowed us to drastically simplify our geometry. And so our manifolding is a lot simpler now. And we have a 2-plate design. During PDR, we presented channels that were circular. They had a circular cross section, and they were part of the channel was manufactured in one plate, and the other part of the channel was manufactured in the other plate. So the combination of the 2 plates put together would give you the entire channel. We've since changed that. So the aux hole, this is not applicable, but the fuel holes, we have a manifold with a rectangular cross section, and the channel is only present on the bottom injector plate, not the top injector plate. Additionally, with regard to sealing, during PDR, we presented a design with a gasket, two gaskets that would hold together, or that would fill the gap in between our two plates, and it would cover the entire face of the plates. But we've since changed that, and now we're using 3 O-rings that we'll get to when we show the actual physical design. And this was mostly because the gaskets we were deciding on were potentially unreliable, and we had pretty small wall thicknesses between our channels. And so we were unsure if the gasket was going to be sufficient to actually hold the pressure. So we moved to O-rings that we can buy commercial off the shelf. All right. This is the overall design for our injector. We have 3 plates. You can see that so going from the top down, we have 2 tube fittings that take propellant input from the feed system. The aux is in the center, and the fuel is off to the side. The top, the highest, the top plate that extends from the diameter extends from the other 2 plates, that is the interface plate, which will attach to the test stand. And those 2 bolt holes off to the sides they will have threaded rods that will attach to the test stand. And we'll get to that later. This middle part down is the top injector plate. I guess the nomenclature was a bit confusing there because the top plate isn't exactly on the top. So I apologize for that. But yeah, the top plate, you can see the bottom 2 plates are the actual injector plates, and then the interface plate just rests on the top. All right, now I'm going to hand off to Aiden, and we're going to go over. Yeah, there's another Aiden. We're gonna go over to the individual design of our plates.
All right. So to get started with the injector or the interface plate, excuse me. Like Aiden was saying, this interfaces with the test stand itself, and it's a separate part because it would save material. It's made out of aluminum instead of stainless steel like the rest of the injector. And obviously aluminum is cheaper per the same amount of volume, so it would allow us to save a lot of money. Regarding the actual architecture of the plate, there are the 4 holes on the outside, which are used to interface with the test stand, and then the 9 holes on the inside, which are used to interface with the rest of the injector plates. All right, moving on to the top plate. So you can see there are the aux and the fuel inlets on the top, as well as the 9 bolt holes, which are going to be kind of constant throughout the plates of the injector. And then if we move on to the bottom view, you can see that there is a clocking feature. And that's just a little slot that allows us to properly align the top and bottom plates with each other so that the holes are properly aligned. And then with the bottom plate, this is the most complicated one. So we'll dwell on this one for a little longer. The first feature I'd like to call out is number 4, which is the clocking feature, like the male component of it. That interfaces with the clocking feature on the top plate. In addition to that, there are 3 O-ring grooves, which are labeled 1, 2, and 3, as well as 3 vent holes, and then a fuel channel and an aux channel, and then of course the 9 bolt holes on the outside as well. And we'll just leave that up for a little bit. Yeah, what's up?
Pretty small.
I think
They're
they're
50,000.
50,000, yeah. Yeah,
Happen.
happen.
It's gonna be probably not stuff. Yeah, it's possible to, you might wanna think about trying to shorten that, the amount of how thin it is. I don't know how that like the injector purposes, how it's not the thin portion doesn't go all the way through. Because it's gonna be buying a drill bit that's 50,000 in diameter, that's that long, we think you're hard to find. And getting used to deal with it is the one other challenge.
Yeah, definitely cool. Something to consider. Thank you.
Thank you.
All right. Any other questions?
For your clocking feature, Was there a particular reason why you made basically a step type caulking feature?
This was just, it's conducive to manual machining, which is what we were planning to make the entire part on a manual mill or lathe. And like we considered doing like alignment nubs that would like interface with, like you'd have a male side and a female side on one plate and the other plate, but the nub features would be too hard to manufacture manually. So we moved to this design where you can create everything using just a rotary table on a mill. Yeah, that was the main thing.
And we'll go over manufacturing a little bit regarding the rotary vise.
So I would just caution you, if you want to view that, then an extra, I mean, that's an extra, an interface where it's the, kind of like a critical dimension where you wouldn't get proper, squeeze on your O-rings if you don't have that, properly dimensioned. Having, two flat plates and then marks on the external and then, controlling your clocking via procedure for verifying that those marks are aligned just on the OD and the thing would save you some machining steps to keep those faces flat.
Okay.
It's a good point.
Thank you.
Thank you.
Quick question from my side. Can you guys hear me?
Yeah.
Yeah, so I'm Ralph from Don Aerospace. I'm got a quick question on your selection of manufacturing process. Why, like, have you considered using additive manufacturing for this particular part?
We initially were considering 3D printing or metal 3D printing, but it's just very difficult to access on campus, if I'm not mistaken. There's only a single one on campus. So.
Okay, have you considered like going externally or like trying to get sponsoring from maybe a company or something like that?
That's something we considered, but we decided we wanted to manufacture it in-house just for the experience.
Oh, okay, just saying that I've manufactured a lot of these things and it's a pain. Like, you know, you're gonna go through a lot.
Yeah, we're planning to break a lot of drill bits. So. All right, thank you. Any other questions?
If hot combustion gases escape up the vent hole, could that affect the O-rings at all negatively?
Yeah, so we're under normal, we'll get to this later, but under normal conditions, the vent holes will be pressurized to the combustion chamber, which is at 10 bar, and the fuel is pressurized to 12 bar at its lowest. So they shouldn't affect it.
There should be still enough pressure difference to sufficiently push the O-ring into the groove and create the seal. So I don't think we would have any problems there.
Yeah.
What are the materials that you're putting in?
The top plate and bottom plate are stainless, 316.
303.
303, right. The aluminum one is for the fitting between the interface, or the interface plate, excuse me. So we go back to this slide. The interface plate is aluminum just because it's so large, and machining it out of steel would be, well, buying that much stock would be expensive.
But it's aluminum, the other two are
Stainless steel, 303, yeah. And we'll get to material selection in a little bit. Any other questions before we move on to sealant?
Maybe one more from my side. Have you considered putting in ports for pressure sensors and stuff?
No, not.
We maybe did a little bit, but if there will be a pressure sensor, it would likely be in the combustion chamber to avoid extra complexity in manufacturing, as these parts are already going to be extremely complicated to create.
Sure, but I might recommend putting one at least on the fuel side, I guess, just to characterize your pressure drop over your injector, because it's one of the sort of, well, it's one of the very interesting things to know. Also, it verifies if your discharge coefficient is sized correctly.
That's a good point. Yeah, I'm unfamiliar with our feed system, so I'm not sure how far upstream there is a pressure sensor. So we could potentially determine it that way. But that's a good point. We could consider that, yeah, because there will be a 90-degree fluid flow change as the fuel will enter the fuel manifold channel, and we don't know what pressure drop that will actually create.
Yeah, similarly, maybe also consider putting a thermocouple. I know it's quite a difficult part of the machine already, but from my experience, it's always very useful to know the state properties just before injection, because that can tell you a lot. Like, for example, for the nitrous, it might also mean that you're in sort of a supercritical region or something like that. You can easily verify that with pressure and temperature.
Yeah. Oh, I forgot to mention back in the high level design, we assumed that we were unsure of the phase of the nitrous oxide by the time it hits the injector. So we assumed that since the orifice is dropping the pressure of the nitrous well below its vapor pressure, we assumed that it's primarily gas, and we assumed a quality of 0.8 in sizing those orifice holes.
Right. It might be quite tricky as if you don't have an orifice restriction somewhere in your system. Because from my experience, if you don't really have that, nitrous will probably be liquid for at least a part, like maybe not at the start, but you'll start getting liquid through at a certain point.
Interesting. Yeah, we were very confused about whether or not it would be a liquid or a gas just because we're dropping it so far below the vapor pressure, but it's also occurring so quickly.
Anything else? All right, and then move on. So the last component is the tube fittings. There are two of them, one for the fuel and one for the aux. These are going to be 3/16 stainless steel Swagelok tube fittings. They're going to be 1/4 inch NPT, and then we're going to add Teflon tape for additional sealing. All right, and then for the O-rings, there's going to be 3 of them, an inner, a middle, and an outer one. And they're all sized according to the Parker O-ring handbook. They're going to be made out of Viton fluoroelastomer because of the high temperature requirements that we have. And then you see the diagram, there's going to be 2 O-rings that separate the fuel and oxygen manifolds. And then there should be a region in between them where the vent holes are. And then the red region is just the region that fuel could escape to, and the green region is the one that the aux could escape to. And they are kept separate by the 2 O-rings. Right, and then the vent holes. So like Aiden was mentioning earlier, it's single fault tolerant. So if one O-ring fails, the propellant will vent directly into the combustion chamber instead of mixing in the injector. We have kind of a hypothetical scenario up on the screen where, like, let's say that the fuel fails, or the fuel O-ring fails, excuse me. So it bypasses the O-ring, and instead of then pressurizing the aux O-ring from the other side, it'll simply vent directly into the combustion chamber instead of causing problems with the other O-ring. And then under normal conditions, the vent holes are going to be pressurized by the combustion chamber to 10 bar, which is less than the pressure inside the injector. So they should still be pressed up against the right wall of the channel. Thanks. Any questions about the sealing and vent holes?
Maybe just a quick comment on the fitting. Any reason you chose MPT rather than something like BSPP with a face seal?
I believe it's just for the extra sealing that the taper provides.
Sorry, could you
Sure.
repeat the type of fitting that you like, the alternative type that you said?
Just a parallel thread, like something like British pipe parallel with a Dowdy, for example. From my experience, Teflon tape is always a bit messy, like it gets everywhere, and it can also end up in your injector, which could block, like, for example, these injector holes. just using like a parallel with something like a face sealing type, like a Dowdy seal. It just makes everything a lot simpler, and you don't have like consumables that way.
Thank you. I'm unfamiliar with that type of thing, but we will research that.
Thank you. Anything else? We have selection. Thank you. Hi, I'm Alex, and I'll talk about our material selection a little bit. Yeah. So we, Aiden found about a foot of 303 stainless steel that we're going to be using. We originally were going to do 304 due to its corrosion resistance, but 303 has very similar properties of 304, namely its corrosion resistance. And we're going with the 303 that Aiden found because buying stainless is very, very expensive, and this would cut down our cost by like $600 or something like that. It's also, I didn't write this down, but 303 is actually slightly easier to machine anyway. For the interface plate, we selected 6061 aluminum. This is because 6061 is the most common kind of aluminum, and the material specifics aren't very, very important for this scenario. So for a manufacturing plan, before we manufacture our final parts with stainless, we are going to do an aluminum prototype. We're going to talk about testing. We're going to do testing on both of those. They're designed to be made on the manual mill and a lathe, so we don't have to do any sort of CNC operation. The channels will be manufactured using a rotary vise on a manual mill. The slanted impingement holes we manufactured by rotating the mill head 45 degrees. And we already talked about the hole sizes, but we'll use a number 40 drill for the aux hole and a number 57 drill for the fuel holes. Our testing plan for both the aluminum prototype and the stainless steel is the same. We're going to do a hydrostatic pressure test. So we're not going to drill the orifice holes, and we're going to pressurize the injector using slow props test procedure. If you don't know what that is, we're going to essentially just submerge the injector in water and pressurize it, wait an amount of time, and then read the pressure and see if there's been a drop. And then for our cold flow test, we haven't come up with a test procedure, but that is we're going to do that. Yeah, if there are no questions, then I can move on. Yeah,
I have a question. So can the full injector assembly can be mounted to the test stand without the combustion chamber?
Yes, you would need either different bolts, or you would also need the retaining ring in place.
Okay.
But actually, no. Yeah, the bolts could just be slid further up, and then yeah. So we could do it.
Okay, because that would be probably the easiest way for the cold flow. To be able to see it would just be to mount it to the test stand.
Yeah.
Could you tell me more about the flow visualization for the full cold flow test?
Yeah, basically the idea is we just want to see if the streams are hitting each other. Like we want to know, like sure you can 3D print and watch your streams hit each other because the 3D printer made it perfectly, but we're manually machining our injector. So we want to know, like, did we really do this correctly? And so we'll flow water through it, through both the fuel and the aux holes at the same time, and then we'll watch the propellant streams and filament, and on both the aluminum part and the stainless steel part, just to make sure that we're actually getting impingement. Because if we're not, then there's the part is a failure. All right, now we're going to move on to the interface plate. Thank you.
All right, so for the interface, we needed it to do a couple of things. First of which being provide sealing between the combustion chamber and the injector assembly. And we needed to provide adequate compression to the injector for the sealing and overall stiffness of the joint. And it also needs to withstand the mechanical and thermal stresses from the pressures and temperatures from the combustion chamber. So we used a retaining ring as opposed to a flange machined into the copper to decrease the overall copper stock size and decrease the amount of material lost due to machining. It uses an angled mating surface to reduce the stress concentrations for both the retaining ring and the combustion chamber. And then the bolts hold the 9 quarter 20 stainless steel bolts hold the whole joint and compression with multiple O-rings for redundancy. So more about the retaining ring. It's machined from the same 304 stainless steel stock that the injector will be made from. It's got 2 seated O-ring channels. You can see the 2 sides of the cross-sectional view, and they're highlighted in black on the bottom diagram there. And in terms of machining, we are going to need special grooving and boring bar tools for the angled interface section and those seated O-ring channels. And we're planning to manufacture that on the same Haas TL1 CNC lathe that the combustion chamber will be manufactured on. So the bolt loading analysis, we followed Shigley's bolted joint analysis for permanent joints. And these are the forces that we considered on the bolts. We have the bolt preload, the propellant pressure, the combustion chamber pressure, the O-ring compression, and the thrust. So the preload was calculated as a factor of the yield strength for the specific fastener. And we also verified that the calculated preload could keep all 6 O-rings in compression handily. Question?
Say, it's going stuff, you're planning on building those threads when you put it together, so then are gonna be able to take this apart, you take it apart. Yeah, use those same bolts to put it back together.
Yeah.
Every time taking apart, getting a new set of bolts.
I think for the permanent joint analysis, we were just, because the preload is higher and it's supposed to be like a stronger joint, we just went with the permanent, like I think it was like 6% more preload for the permanent versus non-permanent. So we're probably not gonna like buy new fasteners every time, but we considered it permanent just to be like a stronger preload.
We also changed, it's a factor of like 0.1, I think, between permanent and non-permanent joints. So it doesn't change our overall safety factor on the bolts all that much. So it's something we might consider just designing it for the non-permanent joint, like you said. Another question?
Why was stainless chosen for this and not aluminum like the other retaining ring?
Stainless was chosen, I think, mostly because we have the stock on hand. So like they said, we have the 303 stock already in the shop, and it was the right, it's already the right size for the injector plates, and our collar, or the retaining ring, is the same, has the same outside diameter as those injector plates. So it's pretty easy to just chop that up into a couple pieces of stock and then machine it from there. At least that's my understanding. I did not select the material in personal, but any other questions? Okay.
Yeah, could you go a slide back if you can, just to see the design, or maybe one more. Yeah, I was just thinking, why don't you just make 2 O-ring grooves in the copper if you're so concerned about a backup? Because now you need 3 seals, where then you just have 2 seals with the same redundancy, right?
Yeah, that's a really good consideration. We are a little bit worried about our seals in the copper, because the copper is going to get a lot hotter than the stainless, or we're predicting that the copper is going to get a lot hotter than the stainless steel. So we are a little bit worried about that seal, and so we chose the 2 backup seals on the in the retaining ring as a backup.
Okay. Also, probably, yeah, just go ahead with it. I'm sort of theorizing that probably the copper will seal itself against the retainer ring, like the bevel. They'll probably have.
That's our hope with the amount of preload that we're putting on the bolts. It will make a pretty good seal with the soft copper against the stainless steel.
It's going to be easy to take apart and fix the O-ring and put a new one in for the technology.
That's a great question. Probably not. in all reality. We might see some of the, we might see the O-ring that's machine, or the one that's machined into the copper. We might see that one melting during our testing. But we did on the thermal analysis a lot of slides ago. We're predicting about 400 to 500 degrees in there after the 3-second burn. And these O-rings should be good to up to 600. So yeah, we're hoping that it'll stand up, but if it doesn't, it will be a little bit hard to replace for sure.
One fire and then we have to take it all apart and then we can put it back together for a different day to try to fire again.
Hopefully.
Yeah, that's probably more suited to Adam as the high level question.
Hopefully, yeah. I don't think we're definitely not. I think we're only trying to get like maybe 2 to 3 firings from the specific thruster. Yeah, because we think the throat will be probably toast after like 3 firings.
Any other questions?
Sorry, could you repeat it? Like you would basically only do a couple of firings for one chamber?
Well, that's what we're kind of expecting. We're expecting the throat to maybe blade a little bit or melt a little bit because we are doing a heat sink, but like not entirely. Our thermal analysis shows that it probably won't, but this is just like a very conservative expectation of not being able to fire this for months and months. We want to be able to scale this fast. So
yeah, just maybe one suggestion from my side is to critically look at the design and see how you can improve your turnaround rate. Like because on the test cell, like you might need to replace O-rings often, especially the one on the chamber. So find a way how you can just quickly do that without spending half a day, like, you know, and doing bolts and nuts and things. Because like everything is now like I think retained with one bolt going through the whole assembly. Like you know, another way to make it simpler is to just have the flange and chamber come off separate from the rest of the assembly. But yeah, like it is a bit of a change in design that way.
Yeah, that's a really good point that I think we'll definitely try to keep in consideration. Thank you.
Yeah, and so then we have a question for the chat. So given the different materials being used, if you look at the effect of the various coefficients of thermal expansions on stresses and your geometric tolerancing?
Yeah, that's definitely, we're trying to run like thermal sims through ANSYS or through SolidWorks, so like FEA, things like that. But we haven't gotten to that stage yet because we haven't made like a pretty reliable model, but it's something we should take into account. So it's not really down the line, but yeah, hopefully we figure out those sims. And to talk to I think Ralph's point. Yeah, we bought a ton of O-ring seal. I think the O-rings come in packs of 50. And we're gonna buy a lot more extra fasteners. So hopefully we can iterate a lot faster and test a lot faster. Yeah.
Any other questions on this slide? Or any other?
Yeah. I think we were okay. Yeah, here we go.
Yeah. Did I finish up the other slide?
Did you?
Oh yeah. Okay. Okay. So we derive the propellant pressure forces from very conservative estimates of the pressurized area on each plate. So ideally, the only pressurized areas would be the channels shown by the blue arrows on the diagram. Instead, we considered basically the event of an O-ring failure. And the green, yellow, and red arrows correspond to the different areas we consider to be pressurized. So these loads, as well as some others, lead to increased tension in the bolts, leading to a factor of safety of 1.1097 for the bolts and an installation torque of 12.2 foot-pounds. Next slide. And then this was the calculations used for all the stuff in the interface, bolts and whatnot. you have any final questions on the interface as a whole?
Yeah, just look at the factor of safety of 1.1 is not a lot. And you also have some additional effects like bolt heating and stuff that will also reduce its strength. It may be just wise to, radically increase the number of bolts you use to go to the safety factor of 1.5 or something that you don't have to worry about it essentially.
Yeah, so I was looking in Shigley's and it talked about the preload stressing the bolt close to its ultimate strengths or its yield strengths, so that your factors of safety that you would see are a bit lower. I know overall we're shooting for factors of safety of about 1.4, but because of that reading that I did, I wasn't super concerned with that factor of safety. But you bring up a really good point with the temperatures. That we might see that drop down a little bit. Would you recommend more bolts or less preload or anything else?
If you want to minimize the amount of work, again, like if you want to test a lot and have to disassemble and assemble it again, it might just pay off going for stronger bolts, like something like 12.9. I know they corrode maybe slightly, but then again, you're not intending to have this as a flight or as a sort of a thing that has to do 1,000 burns or something. So you might consider doing that because that's the easiest way forward. I think 12.9 bolts are like twice as strong as stainless. So suddenly there's no problem anymore.
Awesome. Thank you very much. Any other questions on the interface? Okay. Thank you, guys.
All right. So I'm Matthew, and I'm back up to talk about the feed system, and I'm bringing up Seren and Kyle, who are going to be along with me. And the feed system is kind of shared. So as we're going to go through it, the feed system is going to kind of dovetail into the test stand itself. And so with that, that'll kind of go over a lot of that'll kind of be shared. There's a separate presentation on the actual test stand itself because it is a separate product. And so getting into that, starting with the plumbing and instrumentation diagram that was developed. So Bluegrass is the name of the test stand, and that is going to be covered. And so walking through the test stand, so the general overview is we will be pressurizing both the ethanol and the nitrous separately. So we won't be using nitrous self-pressurization for that. So we have a gaseous nitrogen pressurization system. We will be running down through each of the run tanks, which will be mounted to the test stand. And then along with that, it will be just run through check valves to the main propellant valves, which will be running into the engine. There is a line on the fuel side that is designed for to be compatible with the senior project's liquid engine, which includes a separate fuel line for film cooling, which is why there is that branch off near the thruster itself. And then it has, we will be doing flow metering with Venturi flow meters. And then for safety purposes, there's a lot of safety features which I will run into, but the ethanol is planning to be manually filled for the run tanks, and then the nitrous itself will be remotely filled because there are procedures in place from our hybrid rocketry days to be able to remote fill nitrous that we will be able to use for that. So running into the feed system components. So here's an overall view with the test stand, and this is for the structure of the test stand. It will be going more into it. So the regulators will knock the pressure down, and I'll go back here. The pressures are noted there. So as Aiden was talking about in the injector slide, that's where we derived a lot of our requirements for the feed system pressures. So for the fuel side, we'll be pressurizing to the fuel to 230 psi, where with the pressure drop across the system,
it will reach the injector at approximately 175 psi. And further characterization will be one of the main, further characterization of the actual pressure drop across our system will be one of the main testing goals of our system, because the main pressure drop is actually accounted for in the reduction from going from a half-inch propellant lines down to the quarter-inch feed lines, because one of the big design goals of this plumbing industry of this feed system is to be scalable, and so all of the feed system is designed to be capable of handling a 600-pound engine, a theoretical 600-pound nitrous ethanol engine, that we will be designing to in the future, which will again be talked about more in the test stand. And so with that, so this is a full CAD integrated model of the layout of the system itself. And so it has the stainless steel run tanks, as well as all of the solenoid ball valves and everything there. And then so in terms of the rationale, again, I've talked about most of this before. So the half-inch propellant lines, which reduce to quarter-inch before the injector, that is again to accommodate the future-proofing of the design. And with that, because it is so oversized, there's many design considerations that aren't as important. The mass flow or the actual velocity of the fluid is incredibly small throughout the entire system, ranging from 0.5 to 2 meters per second. Especially on the oxidizer side, this drastically increases the safety from particle impact ignition from the oxidizer side. And one of the main, drivers for this was also the reuse of components that we already have on hand. So because of our extensive past with hybrid rocketry, we have many valves, and fittings and other piping components that can be reused, although they will require cleaning because they have been sitting around in the hangar for many years untouched. So they will need to be thoroughly cleaned before reuse. And for that same reasoning, swage lock fittings have also been chosen because their pressure ratings are well beyond anything that we need. And there was some debate as to whether to choose AN or JIC flared fittings, which would be preferable in this situation because of their sealing capabilities, but because of the pressures that we're running at and the fact and the availability of swage lock fittings that we already have in our connections with Swage Lock as a company, it was chosen to go with Swage Lock for that reason. And then safety features. So one of the most important things for the feed system is this is the primary safety, probably the most dangerous aspect of the engine itself. And so it is designed for remote operation as much as possible, especially during critical operations, which are during nitrous fill and during firing. And so nitrous fill, flowing nitrous is one of the most dangerous aspects of using nitrous as a propellant. And so that is so we have designed the engine to be able to be remotely operated through our DAC to avoid having technicians at the stand while there is a nitrous flowing. So the nitrous tank is designed, because of that, the nitrous tank is designed to have overpressure safety devices, including the pressure safety device, as well as being able to manually vent and manually drain the entire system. So check valves are also used between major components, including before the purge system, before the pressure lines running into the propellant tanks, as well as after the propellant tanks, to avoid any sort of flashback from propagating through the system, or to prevent any sort of propellant mixing through the system. And then one of the other important characteristics is that the stand will be able to fail to a known state, and that known state will be designed to be a depressurized state. So there are drain valves at the bottom of the system which will fail open, which will vent any pressure in the system upon loss of pressurization or upon loss of pressure or upon loss of power to the system. And so that just adds an extra level of safety that we will never be approaching the stand in a pressurized state. And so more safety considerations will also be talked about in the test stand. And so this is kind of a more rough overview as well, because there's more slides on this when we go over the test stand. And so one of the big things for the feed system was the tank sizing, which Kyle can talk about.
Yeah, so this was a pretty simple calculation. We just took our mass flow rates. We had a runtime of 3 seconds. Using that, you can calculate the mass that you're going to need in the tank. And from that, just looked up a table for 90% ethanol at 40 degrees Celsius and nitrous oxide at 36 degrees Celsius, which is its vaporization pressure. And that was its lowest specific volume, or sorry, specific mass, whichever one that was going to make the tanks biggest. Basically, I chose numbers that were going to be, these were the largest tank sizes we would need, and they were both well under a liter. So we just chose 1 liter tank for both of them, which gives us plenty of margin. You can see what around 0.4 of a liter and 0.15 of a liter. So we've got more than half the tank in both of them in case we do have any issues with tank size.
Yeah. And then the last part for the feed system is just talking about how we're going to be able to test and validate the system. So there's three primary test campaigns that we will need to run. The first is going to be hydrostatic testing of each line before it goes in. And so using the same hydrostatic test rig, we are attempting to use some of the mechanical engineering fund has a round of funding to be able to purchase our own hydrostatic test rig, or our own hydrostatic pump to be able to hook up each of the lines, cap one end, and hydrostatically test each line to at least 1.5 times the the expected operating pressure to ensure that none of our lines are leaking before they're installed. The next is the valve characterization, because a lot of the valves that we are using are going to be reused from old systems. We will need to recharacterize them to understand the CV, especially for the main propellant valves, which are the most important for this case. And then the final test will be full cold flow tests. And one of the things that we are exploring is the use of CO2 in the place of nitrous to still get the similar characteristics of two-phase flow that CO2 has without the hazards that are associated with it. Although it might prove to be difficult with the temperature of CO2 and the valve components that we're using, it could prove to be more trouble than it's worth in terms of getting the valves too cold. And then water, in which case we will just use water in place of both propellants running through the feed system. And so that wraps up that. And so then just, and so again, this is this is just the appendix for the pressure loss due to the change in area, which Serena can talk about, just because that is the primary pressure drop across our system. And it was found that because the propellant feed lines are vastly oversized, the pressure drop due to other considerations, it was minimal. So this was the primary pressure drop, and Serena can talk a little bit more about how he arrived at that number.
Yeah, really, like you said earlier, when you look at our feed system, you could basically the biggest pressure drop, just like you said, is in the change in area from going from the 1/4 to 1/2 inch or 1/2 to 1/4 inch, and essentially I like multiple things were taken into account, but this is really just a MATLAB code using Bernoulli principles and just analyzing what area change pressure drop does, and by getting that pressure drop, we can see what we need are. We can also use we have readings.
Yeah.
And
so I guess that will be the other thing to mention is on the plumbing and instrumentation diagram.
of where we are taking pressure measurements. Not pictured are the pressure indicators on the regulators for each of the system, we will use to set the pressures for the fuel and the oxidizer readings. And then below that, we will be taking pressure and temperature measurements for the tanks. Right now, it is listed for the temperature of the tank, which is going to be correlated primarily with the pressure inside of the nitrous tank, and we will be taking a pressure measurement inside of the ethanol tank. And then the other main pressure and temperature measurements will be down closer to the thruster itself, where we will be taking the pressure just after the orifice, as close to the injector as possible, although this will probably end up being further up, closer to the reducer itself. And so that will characterize, so we're trying to get our pressure transducers as close to the injector plate as possible, again, to be able to characterize the pressure drop across the injector as well as possible. But based off of the size constraints and or the space constraints, that will be what's dictating the actual final layout for the system as built. And with that, I believe I will kick it over to Adam to talk about the next steps. Unless there's any questions about the feed system.
Is your feed system sized for your eventual 600-pound engine?
Yes.
And the
So,
tanks as well?
so the run tanks are the only thing that we have not spec, just because we don't want to deal with kind of massive tanks with a tiny amount of volume in them, to minimize like losses and things from the tanks themselves.
Right. All right. These are just the next steps. Very last thing we're going to do before we kick it over to the test stand. A very preliminary cost estimate of our whole system. Obviously, the feed system belts and regulators at like 2,000. That's very may not be accurate because we haven't gone through what works in our catalog right now of existing hardware. We have to do that testing and then decide on whether or not we need to update a lot of those things. But yeah, this is just where we're at. Sure, we probably don't have a ton of questions. Cost. All right, and these are the next steps for the Dulcimer. We are going to procure all materials, and we have some on the way or in the hangar. And then begin manufacturing and clearly defining the spring quarter goals for the component level completions and this total system integration. And then I think another big next step is rigorous test procedure writing, that we really need to emphasize safety, reliability, not just for us here, but for CPS in the future and all of the department. And a lot of the test procedures that we will be writing kind of will bank off of a lot of existing test procedures that CPSS has had a lot of experience with in the past. So we will try to use as much knowledge that we've learned throughout. Oh, using a little fire emoji. But begin testing all components and verifying our system meets design parameters. And that period at the end was a fire emoji. But yeah, that's our last goal, is to actually fire this. So yeah. All right. Any questions for the yes? Not clearly defined. That's one of the next steps, is to actually make, because a lot of it has to deal with like when the lathe at the airport is available and will meet our schedule. So I don't want to say system test by a certain time and not even have the combustion chamber machined yet. But yeah, basically it from the engine component level. Next, we'll get into the test stand. Are we going to be taking a break in between?
I think
Yeah, we are making pretty good time. Yeah, so next I will be bringing up the ground support team for our test stands. Johan and Ryan.
I'm Johan. I'm the ground support lead. Ryan, I'm the responsible engineer on the test stand.
I'm Will. I did a lot of the structures.
Starting with that.
So just to quickly go over what the goal of the test stand is, and it's to facilitate the firing of our Dulcimer engine. So the test stand is spec'd out to up to the 600-pound engine, and it's designed to be able to be disassembled, moved between facilities, potentially being mounted on a trailer. It's designed to deliver force data in the thrust direction, pressure data from the feed systems, temperature data from various parts in the system as well. And we'll be able to interface with our engine and the senior design team's engine.
All right, so that image there, that's the finalized design that we have for our test stand currently. It's a vertical orientation, and that's to ensure some safety. We don't want any propellant stuck in the feed system at any point. So this will allow for them to just flow through the whole system. And it's also a little bit easier to use this and disassemble them into like pieces that can be moved individually. It's made out of the 40 series 80/20 aluminum extrusion, and it has a overall dimension of 154 centimeters tall, which is just under 5 feet, 140 centimeters in width, and 80 centimeters in depth. That's about a little under 4 foot in width, and then like a 2 feet, 2.5 in depth, I think. And then if you looked on that model, there's fastening all over the place. We're going to be using L brackets, T brackets, 90-degree braces throughout the whole system. And we're going to be using M8 16 millimeter screws for all of the T-nut attachments. And that's how all of those plates and the 90 degrees are going to be mounted, is with 80/20 T-nut mounting fixturing. And we are also going to be using an end fastener screw, which is what's pictured kind of floating in the middle there. That is going to be threaded. That bolt is going to thread into a tapped end on the vertical portion of the aluminum extrusion. And then 80/20, that bolt slides over 80/20 rail, and the force that is exerted on the test stand axially is going to be pushed into those threads. So hopefully that makes some sense. But those 4 corners on the very top will have threads and bolts going down, and that's where the force is going to be transferred, at least a lot of it. And I know that threads, well, having force go through aluminum threads is oftentimes not a great strategy. So I wanted to go through and make sure that the stress we were seeing was not going to cause failure of those threads. So we ran a calculation, and we assumed the worst case scenario for all of our factors, like the preload and some other factors like the lubrication and some coefficients. And we just assumed the worst for all of it, so that it was the worst case scenario on our aluminum threads. And we found a factor of safety of 1.8, which is still pretty conservative. And that's not including the L brackets and the 90-degree brackets that are also in place on that and that same part, also taking some of that force. So we should be well over a factor of safety 2 on the most critical portion of the stand.
And a big design consideration we had when designing the stand was that moving it past 25 pounds into 600 pounds or higher, we may not be able to test on campus. So we need to be able to transport the stand to other locations that would permit that sort of testing. So the test stand itself, the structure is designed to be semi-modular so that individual components can come off without having to disassemble every single joint. So there's minimal disassembly required to be able to take it apart and reassemble it. And the largest dimension there you can see is the side cross, like the side supports.
Those each come off as one big piece, and those are 5 feet by 1.5 feet roughly. So we should be able to fit this in like a back of the truck or an SUV pretty easily to take it back and forth between locations for testing.
How's it connected to the floor?
Oh,
That's a good question. We are still kind of in the process of determining a very like finalized version of that, but the thoughts that we've had have been like a steel beam or some other additional beam that will go across the legs at the base, and then we can either add chains to that or some other sort of fixture. And we have concrete bolts in the prop slab, which is where we're going to be mainly firing this with rings on them, so we can attach to those and then exert a force down to clamp this whole stand down.
Additionally, we do have some actual steel tie downs that are in possession of the club already that we can attach to the stand to like physically rigidly attach it as well.
yeah. So it'll depend on where we're testing, I guess. So we'll have to design it.
Quick question for me. What's sort of the load that you size it for? Like, because I heard you say that you want to test larger engines in the future. Has that been taken into account in the test bench design?
Yes, we designed our stand to withstand thrust of 600-pound force with a factor of safety of at least 2.
Mm-hmm. Just keep in mind that also design for anomalies, like for example hard starts. I know 2 is probably fine, but just keep in mind that often there's unexpected loads on the test bench, and you just want this thing to be super robust. So like what I usually do is take a safety factor of well above like anything that's reasonable, because you only want to build it once and you don't want to care after that anymore.
Yeah, and we'll go into a little bit of the analysis on the stresses. We did some FEA, and we found that we should be in a pretty good region for our factor of safety.
Can you guys hear me?
Yeah.
Yeah, go ahead.
So this Ryan Sellers, I was concerned. I haven't seen an image of it fully mounted up with the load cell and the thruster, but I don't see any cross members other than at the very top and the very bottom in that vertical space. I know the desire is to have it very open, but if you have any loads that aren't strictly vertical, I see it kind of shearing over and not being very robust in that way.
Yeah, I agree entirely, and that is something that in our PDR presentation we had a cross-section beam, and that was going to be on like a linear rail system, and that would be allowing for some rigidity in that like compression direction, I suppose. But we have removed that for this specific like CDR because we're just going to be using this at least like in the short term for the 25-pound engine, and we aren't expecting to have any issue handling that thrust with the layout we have now. When we move to bigger engines in the future, we are going to need some additional structure. We're going to have some, and that's part of why we chose the aluminum extrusion. It adds some modularity, so we can add some additional like structure to it as time goes on, as we need. So that would definitely be a consideration, as it's like a horizontal beam on a linear rail type system that can help to support the engine and those off-axis forces.
Or even a steel cable in tension diagonally across the space that you could remove if you needed access. But it sounds like you guys have thought of it.
Yeah, and I hadn't thought about that before. That's a good idea. We'll consider that.
Yeah. And then as for practical testing to supplement our FEA and theoretical analysis, before we move to 600 pounds and higher, we'd like to eventually be able to physically test it. So we were thinking the method is to be determined, but we're thinking pulley system, hydraulic jack under the stand, but we would like to be able to load it to physically rate it to those forces before we actually put an engine on there and cause any safety concerns with testing it first time using an engine. And this is the bill of materials for the structures. It totals to about $1,400, which we think we can cut some cost in certain areas by reducing steel plate thicknesses. And also we're gonna have a lot of steel plate scrap after we make our flame diverter and our force plate. So we could make some of our L brackets and stuff ourselves using the water jet instead of buying them from 80/20. So there is some cost to be cut there, but this is the worst case if we buy it all. And the flame diverter plate, the price is still to be determined because that's going to depend on what gauge of steel or aluminum we're able to acquire easily locally. Because that's going to be an expensive part if we make it out of steel bought from McMaster, or for example. So we want to cost that later. And then this is the FEA we did on the engine. We assumed it'd be 600 pound force on, we did a 1 by 1 inch area under the gantry plate as kind of a worst case concentrator. And you can see the high stress regions are kind of on the edges of where the 80/20 meets the cross member beams. There's some stress concentration there. And the displacement graph there is 200 times. And you can see there is some flexing in the middle, but the displacement there is really, it's 200 times exaggerated. So we're not seeing much displacement at all for 600 pounds. So we expect that moving into the factor of safety, that we have at least a factor of safety of 2 going by the minimum mesh element, but we expect we have a factor of safety of much greater than 5. If you look at the mesh as a whole, because those stress concentrators right there on the corners are really only about a factor of safety of 6, and the factor of safety of 2 minimum was found from like 2 individual mesh elements. Any questions?
All right, we'll go into the feed system integration. So we've seen a little bit of this already, as Matthew brought up the feed system, and that image was up there of the feed system integrated onto the test stand. But just to reiterate, the test stand, the feed system is the bridge between the test stand and the prop system, and that's it's going to need to be modular so that in the future we can it's going to need to function for larger engines as well as a small engine, and it needs to allow for all of our plumbing and our valves and our sensors and whatever else we need for all sorts of engines that we're going to be putting on it. So this is the actual CAD design of the implementation of our feed system, like PNID. The test stand is actually like inverted. If you look at the PNID, the pressurant is going in at the bottom of our test stand through a T, and then that nitrogen pressure is going up through regulators and then through ball valves, through hand valves, check valves, through the run tanks, and then there's pressure relief valves, manual fill valves for the ethanol, the automatic fill ball valve for the nitrous oxide, and then those go through again, more check valves, more pressure relief valves into the venturis, and then up into the run valves. And then we have the nitrogen pressurant that's branching off from the initial supply, and that's going to be used to actuate our ball valves throughout the system. Well, it could be used in the future to actuate our ball valves. We're going to go with shop air for now while we're working in the prop slab. But the nitrogen there, the tee off there, is to purge our system once we're done running. It branches off and can purge through the rest of the system. Any questions on this before I move on, or should I leave it up for a little bit, maybe?
So the liquid is going upwards, right?
Yes.
And so I assume you have some kind of tube in the tank to facilitate that, or?
That is something I hadn't thought of. Is that a necessity?
Well, as in like if gravity will just have the gas sitting on top. So I mean, if you want to have liquid going upwards from the tank, then you need some kind of system to be able to facilitate that, right?
Yeah.
At least your friend, use it for everything, yeah.
Yeah, and that's one thing I know this is going to add a lot of complexity having to push our propellants up and over. And I expect that we're going to have some problem solving to do on this front. Like you just brought up, I hadn't thought about that, but yeah, we're going to need to figure out a way to push that liquid up instead of the gas just going around. Yeah.
Yeah, it's a very counterintuitive way to do it. Usually you do it the other way around. You have the gas coming from the top, pressurizing, pushing the liquid down. It might be worth just looking into whether you can make that work, because like also having gas coming from the bottom into your liquid, it might like mix the liquid with the gas quite a lot, and so that might also give you some problems. So yeah, it's a bit of a weird way of doing it.
Yeah, and so maybe it would be better to just route the pressure up to the top, and then still have the propellant lines go from the bottom and then up and over that way, at least from the run tanks.
Yeah, I would definitely suggest that. Also, for gas, like for your regulators and stuff, you just don't want liquid going like might have the potential of liquid coming back through the nitrogen cylinders and stuff. That's just that's asking for trouble.
Yeah, it's riddled with check valves that would hopefully mitigate that issue, but yeah, I could see that being a problem if we don't orient this correctly. Any other questions or comments, Derek? Yeah. There's a different view here, and this is just kind of reiterating more of a isometric view of what we have. And this, you can also see the feed system feeding into the actual injector, and the end of this will be flexible tubing. So up and over from the run valves, that will be flexible 1/4 inch or 1/4 inch tubing for this engine, and then whatever else we need in the future, we can change that as need be, and that'll just go bend around into our injector.
Yeah, maybe one slight concern from my side is there's one rod holding the engine to the test bench. Seems like there is a high potential of like deflection and vibrations and stuff. Have you considered making that shorter?
Yeah, I think in reality we will make that shorter. It's kind of long here just to more or less visualize everything with some spacing, but in reality it would be closer together. And that I'm going to talk about that next, the engine interface, but that bolt is 1/2 inch. So it, at least for this 25-pound engine, I don't foresee any issues with any off-axis forces deflecting that 1/2 inch steel bolt. But in the future, we would have additional guidance of our engine, like a horizontal beam on the linear rails that we were talking about, or something along those lines that would further constrain the motion of the engine and ensure that it's just purely axial, or at least to the best of our ability.
Yeah, that sounds about right. Just a good question. Are you going to go into the filling procedures as part of this presentation, or is that?
Yeah, that will be talked about in a couple slides. I'm going to go through the engine integration and then some DAC stuff, and that'll follow.
Okay, perfect. Thank you.
Where are you going to mount your camera system?
That's a good question. I guess we'll have to see what the best views are. Probably in the upper corners, I would assume.
But wouldn't you want a direct view of the exit nozzle?
Yeah, that's true. If we're firing this in the prop side, we should be able to set up like external cameras as well, on like tripods or on some sort of structure in the prop side. But we could probably attach cameras to those horizontal members and to the top of the stand and get different views and watch the whole feed system and engine interaction and keep track. move on to the engine integration. So clearly this is the deliverable of our test stand, is to integrate with the CPSS engine and the Senior Project in liquid engine, and then any future engines that we develop. We have right now that steel plate is the main like interface point between the engine and the test stand, and then all that hangs from the load cell so that we can get measurement on the force. And while this design that we have currently will work for the Senior Project team and our current CPSS engine, if we are going to be building bigger engines, modifications will be needed to the stand and probably to the interface method in order to make sure that we don't break anything. But here's the visualization of that. So we have that square plate that's hanging from the load cell, and then we just have those 1/4-inch threaded rods through the interface plate that's on the injector. And we have it suspended, so we have enough room to get through our feed system lines, and then the force will be transferred through those rods and then into the main 1/2-inch steel member that will go into the test stand structure on the top. And that's the steel plate in the right picture is the bottom of the top plate of the test stand. Any questions about that? Yes.
Load cell off until right before you test, so it doesn't get.
If we took off the load cell, we would have to detach the feed system as well, at least from the engine, because then that whole component would come down. What we could do is we could have some sort of stand-in for it though too. We could have like a aluminum block that we machine threads into, and we can suspend it, and then we can switch that out for the load cell before we test, something along those lines. But
Yeah. Load cell and right in there.
right, so we don't have weird forces on it. Yeah. Okay. Any other questions or commentary? Yeah.
Why you decided to get rid of like the force slider?
Yeah, the reasoning for that, as far as this iteration of the test stand goes, is that it would add a lot of complexity that I don't think is necessary for this stage. If all we're going to be seeing is somewhere in the range of 25 pounds of thrust, I don't think a 1/2-inch steel bolt will have any issue handling that force, even if it's off axis. Especially if we kind of minimize the length, like we were talking about earlier, and we want to allow for that in the future, but the price and the complexity from that are kind of prohibitive to doing that on the timeline that we have set.
Yeah. Yeah. So that makes sense, but investor, I agree. I agree. We're worried about the load cell.
Yeah, and that's a good that's a consideration that we should definitely take into account. I don't foresee it being an issue for this engine, but in the future for sure.
Yeah. So also from the chat, just the side mount igniter will help or will affect the single force line of action on the load cell. And you'll also need to route the igniter wiring.
Yeah, that's a good point. That's something that's been kind of a newer igniter design. So that imbalance is new. So this, yeah, I think with that we might have to go through the design and look at some do some testing as we get there and see, if we put force on the structure or on the mounting plate for the engine, are we going to have any issues with that? And if so, we'll probably have to implement some sort of control for that off-axis force.
Question for me. The purple lines, are they hard lines or are they going to be flex?
That'll be flexible. The purple here just from the SolidWorks tube routing, because flexible tubing is difficult to do in SolidWorks, and this was meant, just as a visualization more than anything, but those will be flexible.
Okay, perfect.
Any other questions? Hand it off to Johan.
Okay, so I'm going to talk a bit about our DAC system, integrating our sensors and getting data from that to the props team. For main thing that we're using right now is our old National Instruments stack from the hybrid rocket feed system. And that currently has 16 single-ended channels incorporated into it. Right now, in terms of sensors, we were kindly donated a S-beam load cell by Takuna Systems, rated to 50 pounds. The load cell is designed to be switched out depending on how much force the engine is producing, so we can get better measurements of the thrust. We have at least 10 PTs, pressure transducers, measured up to, it should say, 1.5 kilopascal, or sorry, not kilopascals, KSI, not 15,000, but we'll have at least 10 of those, all monitoring different parts of the feed system and flow meters. And then we'll have at least 2 different thermocouples. One is planned to be on the outer housing of the combustion chamber, and the other is planned to be monitoring the tank temperature of the nitrous. And for acquiring all the data from the DAC, we'll be using LabVIEW. So one of the things we wanted to make sure was that our DAC's sensitivity and resolution was lower than the rated precision of our instruments. So for our load cell, we did some calculations based on the given specs, and we found it to have an uncertainty of about ½ pound, which is kind of a lot for a 25-pound engine, but this is about as good as we can do based on the specs they gave us. But the main thing we wanted to make sure was that the DAC itself was sensitive enough so that its uncertainty measurement would be much lower than that of the hardware itself, which is what we found. The DAC sensitive to around 6 microvolts, which is plenty, all things considered. And then for the pressure transducers as well, that should say 1500, not 15,000. So move the decimal place over on the uncertainty. So there's a resolution of about 7.5 psi based on the specs of the sensor. And then checking with the DAC system, we found that there's plenty of room. So again, move the decimal place over 1. So I'm going to hand it off to Ryan here to talk about our safety procedures.
Yeah, so as has been discussed earlier, safety is going to be huge because this is the club's first liquid bi-prop engine. So as far as the test stand itself, there are going to be various safety mechanisms. Some of those being check valves and relief valve, both of those having both types just used for redundancy. Will be used in case of any excess pressure or any other feed system issues, so we can just easily depressurize the system. There'll be a blast plate, as you saw, to guard the main ethanol and nitrous tanks, and as well as the rest of the feed system. So act as a shielding in case of any failure as well, to protect hopefully the feed system. And then a flame diverter at the bottom, redirect any excess, all of the exhaust gases away from the ground and any sensitive equipment. And as far as general safety procedures, storing the tanks in cool places away from combustibles, especially the nitrous. We'll have various safety procedures, kind of talked about some of these already, such as the remote filling for the test stands, the procedural checklist, which will be on the next couple slides of rough procedures for monitoring the values, filling and pressurizing tanks and filling pipes. And then we'll make sure to incorporate different check values, go, no-go values. An example here is, as talked about, we want the safety or the mixture ratio of 1.5. So we'll make sure that the relative run tank pressures will create that mixture as well. Additionally, just using common sense, ensuring that everyone is aware while we're performing the test, ensure that the area is clear when the system or before the system is pressurized. No one should be in the test area while that's going on. And if there is any nitrous leak, the procedure is just shut down any active engine operations, immediately evacuate, ventilate the test area, and get medical attention if someone is feeling unwell. And then the testing procedures. So the testing procedures, this is just a rough procedure. We'll make sure to finalize these, make sure every detail is finished before actually testing. But it begins with just opening the propulsion lab doors so that we can have it ventilated. Ensure that the test stand and fill tanks are secured to the ground, as talked earlier. We'll then secure the engine to the test stand connected to the feed system. We'll confirm that the DAC and any other measurement devices that we have going on are operational, getting correct values. We'll connect the nitrogen supply to the test stand and to the feed system. We'll confirm that the pressure valves are closed. There's no pressure downstream of where the main pressure valves are. We'll confirm, and then finally we'll confirm all the hand valves are in the proper testing position. At this point, we'll make sure everyone that is going to be running the test is ready at their designated station away from the test stand, because all further procedures are going to be run remotely from the testing room inside of the props lab. Procedures. So in order, we'll fill the ethanol tank first, and then we will perform the nitrous fill, confirm that all the pressures using the DAC and the measurement devices, make sure that all of these pressures are nominal. Ethanol run tank should be regulated to 230 psi, the nitrous run tank to 800 psi, and the pneumatic valve regulated to 200. We will fire the igniter before the propellant valves are open. Make sure that the igniter has ignited and is functional. Then we will open the propellant run valves to begin the engine fire. After we collect all the data, we'll open the vents and dump valves to release any remaining propellants, open the purge valves to purge the system with inert gas, and we'll wait a minimum of 5 minutes before re-entering the testing area, just to make sure that all of the propellants are out. I think moving on to manufacturing from.
Yeah, so I'll be talking about our initial manufacturing and timeline plans.
I have a go back on the safety procedure. So you guys expect the nozzle to deform and yield a little bit over the course of your 3 maximum firings. You're going to want to get as much at it as you can out of this thruster. Do you have any sort of inspection? I don't see one listed in this test procedure of the nozzle. Is there any way to have a go, no go check on the nozzle after the first firing? Such as like a mechanical gauge that's stepped or something to inspect.
That is a good suggestion. I think we could definitely incorporate something to check whether the diameter is, I guess, where we want it for firing. But yes, that's.
Yeah, I mean, as of right now, we should definitely add that into the testing procedure, but I think we were just going to measure the throat with calipers or something like that to make sure that it's what we expect. And there was no like ablation of the copper, but yeah, it's a good point.
But also have an agreed upon limit beforehand so that you're not, having the problem of groupthink. Yeah, I think we'll be okay, and then proceeding when you're not.
Yeah, like if it's hit like certain deformation, we'll make sure not to.
Yeah. We'll definitely look at the whole expansion ratio too, like the exit area of the nozzle and the diameter of the throat, to make sure we're getting like the proper expansion that we want of the combustion gases through the throat or through the nozzle itself. So.
I might have missed it, but like, how is the actuation done for like valves and stuff?
Actuation. Johan, you want to? Okay.
Yeah, all the. Oh. Yeah, all the valve actuations is gonna be done with shop air. All ran off of, all ran off of the air in the propulsions lab. And yes, Matthew?
Yeah, but in terms of like actually electrical actuation, it'll all run through one of the National Instrument devices. It's a digital input output device, which will handle the actuation through a relay board to the valves.
Okay. Do you have some kind of like red button that is just separate from everything else you can press in case something horribly goes wrong?
Yeah, not currently in the design, but that's planned to basically just have an all stop button.
Yeah.
In our like in the firing or in the computer area. As part of our checks, we'll have it just an abort button.
Yeah, definitely recommend that, and make sure it's separate from like your primary actuation system. Just if that fails or if there's some kind of computer bug or something like that.
Yeah, it's the button's planned to be completely separate from all like the DAC stuff. So so in the event that we notice something wrong, we can hit that and it will open up all the vent valves as necessary.
Yeah, cool.
So continuing on with the manufacturing and timeline. So most manufacturing should just be cutting aluminum extrusion, and we'll do that with the chop saw, with the metal chopping blade. And for the blast plate and flame diverter, since they're possibly thinner, we'll be using the water jet, but the water jet shouldn't have issues cutting like thicker steel plates. But the sizing of the blast plating might be a limiting factor.
Yeah, so one thing, I have a question, because these are, like, most of the blast plate and flame diverter are pretty simple shapes to cut, and the water jets on campus are notoriously unreliable. But if you talk, like, is there other ways that we could manufacture, like, cut these plates? If you know of?
We were thinking plasma cutting, but that seems unnecessarily complex for.
And then what might take a lot of time, but is possible, is just a bandsaw, and we could cut out the rough outline of it that way. Or even we have the acetylene torch. We also have probably, I imagine we have cutoff wheels on like a grinder or something like that we could use. There's other ways that we could go about it. But water jet, if we could actually get it, would be like the fastest and easiest to use.
Yeah, and speaking of bandsaw, that's what we're going to use for the upper push plates and the motor plates, since they're smaller and simple to like just do it. And so most manufacturing would just be making sure the aluminum extrusions are aligned and screwing in the T-nuts effectively. And onto timeline. So our deadline is May 5th. So that leaves us with not a lot of time. So we need to start ordering this week. And hopefully, since the structure building materials is complete and that's ready, so we'll start ordering that this week. And instrumentation is still in work, and we're still in communication with Swagelok for feed system sourcing. So materials will hopefully arrive in about 2 weeks to 3 weeks, but that also coincides with finals and spring break. So that won't give us a lot of time for that. So our deadline for finishing the structure will be April 5th, and that gives us a lot of time. And that also allows for the feed system hardware to come in.
Yes, Ryan. I expect that we might have some issues with feed system components, certain feed system components. I think we have, I would say the DAC stuff, but I think we have a lot of that already spec'd out with just the things that we have already. But yeah, maybe some valves that we need to order would take a couple weeks to get here. But hopefully we can account for that and assemble pretty much everything else outside of that, and then just, you know, kind of plug and play those in when they get here. And that's, you know, the CAD model that I developed. The valves on it aren't the exact valves, but they're pretty analogous to in the size and dimension, like the shape, so that we could hopefully kind of get an idea of where we might place things.
Go one slide back.
Any questions? Any commentary for us?
Yeah, maybe just a suggestion from just speaking out of experience. For testing, make sure you take pictures of everything before you test as well. Like when you assemble things, when you when you install it, everything else. Just because like if you have a failure, it's always good to know like what the state of the system was before you installed and stuff, so that you make sure that you can sort of eliminate failure modes very rapidly that way.
Okay, yeah. I will definitely be doing that. We've taken a lot of pictures already of just the stuff that we have and past stuff, so we'll continue that.
Make sure you have all your MS data.
Oh, yes. Yeah, we'll need that.
But we need to order right away, have it here in 3 weeks when we get it for it. Yeah.
We'll add that to the agenda.
All right, well then if that's it, at the last, I think the last bit of the slide is just the thank you all for coming. And thank you for being here in person and for everybody showing up on Zoom. I know the time difference, of course, Ralph for coming in all the way across the world. It's been a lot of good feedback today, and I think thank everyone for coming. And so with that, we have some of the rest of the slides are just a lot of appendix. But with that, we can move into design and or into manufacturing to hopefully start to get the ball rolling. And so again, thank you for coming after this. I don't know, Adam, you did.
No, that's it. Thank you, everybody. Yeah, hopefully we figure everything out.
Yeah.